Welcome to The Explainer. I am so thrilled you're joining us today. Look, we're tackling a really critical visual topic for your Cambridge IGCSE math exam, specifically Syllabus 0580. This focused explainer is going to help you systematically conquer those tricky symmetry questions. Whether you're staring down an upcoming exam or just want to strengthen your geometric intuition, we're going to break down both two-dimensional and three-dimensional symmetry so clearly that the answers will literally jump right off the page for you. We're relying strictly on the core syllabus materials today to get you the absolute essentials. Oh, and real quick, before we jump in, make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. All right, let's get into it. Okay, let's dive right into our agenda. As you can see, we're following a sort of dimension escalation arc today. We'll start flat with 2D line and rotational symmetry. Then we'll step it up to 3D planes and rotational axes, and finally we'll wrap it all up with a foolproof cheat sheet.
Section 1. The Symmetry Mastery Blueprint. Let's quickly get our mindset right for this.
Moving to Section 2. Mastering 2D line symmetry. We've got to conquer these flat shapes first, because this is literally the foundation for everything else we'll cover.
So, by definition, a line of symmetry divides a two-dimensional, flat shape into two perfectly identical, congruent shapes. Now, I want to strongly emphasize that word for you, congruent. That is an absolutely vital Cambridge keyword. It doesn't just mean kinda similar or roughly the same area. It means the two halves are 100% identical. Think of it like a fold. If you were to fold the shape perfectly along that line, the two halves would overlap flawlessly. No edges sticking out, nothing. Just a perfect match.
And this brilliantly illustrates how some of our most common shapes possess very specific numbers of lines of symmetry. Take a kite, for example. It's got exactly one line of symmetry right down the middle. A rectangle or an isosceles triangle, those give you two. Step it up to an equilateral triangle where all sides are equal, and boom, you get 3 lines of symmetry. And a square, perfectly symmetrical on all sides and diagonals, gives you 4. Honestly, getting these foundational numbers locked into your memory is your first key step to exam success.
All right, Section 3, 2D rotational symmetry rules. Now that we've got folding down, let's see what happens when we start spinning these flat shapes around.
A shape has rotational symmetry if it looks exactly the same as its starting position when it's rotated. But notice the specific phrasing here. It's rotated about a central point. I want you to imagine a pin stuck directly into the dead center of the shape on a flat piece of paper. As you spin the paper around that pin for one full 360-degree revolution, you're just counting the number of times the shape perfectly matches its original outline. That count? That's what we call the order of rotational symmetry.
So, let me challenge you directly on this. What do you think is the order of rotational symmetry for a regular hexagon? Seriously, visualize it for a second. Imagine spinning a 6-sided regular hexagon around a pin right in its center. How many times will it match its starting position in one full turn? Keep that number locked in your head while we reveal a little mathematical cheat code.
Well, if you guessed 6 for the hexagon, you hit the nail on the head. You were absolutely right. Looking at this data, an undeniable pattern emerges for regular polygons. Check this out. For an equilateral triangle, it's 3 sides, 3 lines of symmetry, and an order of 3. A square is 4, 4, and 4. A pentagon? 5, 5, and 5. The regular hexagon is 6, 6, and 6, and it goes all the way up. A regular decagon has 10 sides, 10 lines of symmetry, and a rotational symmetry of order 10. It's a beautifully simple rule. The number of sides perfectly matches both the lines of symmetry and the rotational order. That pattern right there is going to save you so much time on an exam.
Moving right along to Section 4, Slicing 3D Shapes. We've mastered the flat world, so it's time to add a dimension and look at planes of symmetry.
Let's see how this builds on what we just went over. When we compare the 2D rule with our new 3D rule, you'll see that in 3D, we aren't using lines anymore, we use a plane of symmetry. Now, a plane acts exactly like a 2D line, but instead of being a line drawn on paper, think of it as a perfectly flat sheet of glass cutting straight through a solid object. And just like the 2D line, this 3D plane must divide the solid shape into 2 completely congruent solid halves.
Let's use a standard solid cuboid, like a brick or a shoebox, as our example here. A cuboid has at least 3 distinct planes of symmetry. You can slice it horizontally straight through the middle, vertically right down the center, or crosswise. In each of those 3 distinct directions, the plane perfectly divides the solid shape, leaving you with two identical, congruent, solid blocks. Pretty cool, right? Okay, so we've successfully sliced our 3D solids, but now we've got to figure out the rules for how they spin. Welcome to Section 5, 3D rotational axis. Now pay attention, because this is a crucial Cambridge distinction where students so often lose marks. While 2D shapes rotate around a flat central point, remember our imaginary pin, a 3D object doesn't spin on a dot. It spins around a central axis. This is an invisible straight line that completely intersects and passes right through the solid object. The absolute best way to visualize this is to think of a classroom globe spinning on its stand. That metal rod going from the North Pole straight down to the South Pole, that is your central axis.
Let's apply this axis concept to our cuboid again. I want you to imagine a central axis pierced straight down through the top and bottom of a rectangular cuboid. If you spin that solid block around that axis, just walk through the mental exercise with me for a second. As it completes a full 360-degree rotation, how many times does the shape look exactly like it did before you moved it? Well, it's going to match its starting position exactly twice. Therefore, we'd say a cuboid has rotational symmetry of order 2 about that specific vertical central axis.
And that brings us to Section 6, the symmetry cheat sheet. Let's bring all these dimensional rules together into one final mastery framework for you. So let's do a quick recap of the really crucial points from this dimension escalation. First, 2D lines divide flat shapes into identical congruent halves. Second, 2D rotation always happens around a single central point. Third, and this is a big one, never forget the regular polygon pattern. The number of sides equals the lines of symmetry, which equals the order of rotation. Fourth, stepping up into 3D, plane slice solid objects into congruent solid halves. And finally, 3D rotation happens around a central axis, that invisible line piercing right through the object.
To wrap things up, I really want to leave you with this final thought. You now have the tools to dissect the geometry of literally everything you see. If you can fold a flat shape perfectly in your mind, spin it on a point, slice it like a solid, and rotate it on an axis, what other hidden mathematical structures are waiting to be uncovered in the shapes around us every single day? Keep looking at the world through this powerful mathematical lens, and I guarantee you'll be completely prepared to ace any symmetry question the exam throws your way. Thanks so much for joining me on this explainer. And hey, before you go, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Keep observing, keep analyzing, and I'll catch you next time.